Welcome to ePathchala lecture series in computer science. We are discussing the paper Cryptography in Network Security. In this module, we are going to discuss about Simplified DES, Data Encryption Standard (SDES). The objectives are to learn about simplified DES process and also what are the steps involved in the each round of encryption and decryption. In addition, we are going to discuss about the key expansion process in the case of your simplified DES. So, we all know DES is a data encryption standard as one of the first algorithm of modern cryptography, and also it is widely used till 1996, and it is also a symmetric key cryptographic algorithm. So, DES became a federal standard in November 76, that is NIST, National Institute of Science and Technology, where the hardware standard is in January 77. So, ANSI where they have hardware plus software, ANSI were X 3.106 where they given the modes of operation. Australia they have having the version AS 2805.5 in 1985. Used in most of the EFT and EFTP for banking industry, it was reconfirmed as the standard for 5 years twice. Currently, we are having triple DES which is recommended. The standard in public, so the standard, what is the standard of DES is public, the design criteria is classified. That means, whatever the standard anybody can able to use it, but they never revealed the design criteria of DES algorithm. One of the biggest controversy is the key size. We all know the DES key size is 64 bit, but every 8 bit is removed, the size is only 56 bits. Where Duffy and Hellman they use an exhaustive crypt analysis of NBS, National Bureau of Security data standard, data encryption standard, where they break the algorithm, and they say DES will be totally insecure within 10 years, which we can able to refer with IEEE spectrum in 1979. So, another controversy is there any backdoor attack? So, we say DES is a data encryption standard where it is going to be one of the symmetric cryptographic algorithm, but it has one of the biggest controversies is that key size. DES has proven a well designed code, and 56 has been proven inadequate. EF built a cracking for around $2 million. They increase the key size to 112 bits. The best way to know about crypt analysis of DES is a differential analysis. National Security Alliance News, there is this forms the design. So, DES operates in 64 bit block with 56 bit keys and uses 16 round, each computed by a function f. So, apart from this information, we already know about this algorithm. This algorithm uses 64 bit block with 56 bit key, and also it has 16 rounds, each round is computed by a function f. This is what our overall idea of your DES algorithm. So, now we need to understand what is simplified version of this, how we can able to easily understand the working principle of this data encryption standard algorithm. So, for the study purpose, there is some topic which is discussing about this simplified DES. Instead of using the 64 block data and 56 bit key, they use smaller key and smaller block of data with less rounds, so that we can able to understand the principle, working principle of data encryption standard. And also here this is providing a overall structure. One thing we can able to understand here is, this is our data block, that is 64 bit, which is divided into two half, 32 and 32, left half 32, right half 32. And also we can able to see here the R, a copy of R is directly transferred into L of other round. This we have observed during the data encryption standard algorithm. So, if I am taking a right half, it is not go through any operation, you can see here no operation, just swapping of bit. That is also another weakness of this algorithm. Each and every round the right half is not undergo any encryption process, simply it is swapped to left half. Whereas if I take left half, that is L I minus 1, it is directly adding into the right half to generate new right. That means the operation is this 32 bit alone going undergo encryption operation under each and every round, this L half alone going to be modified, whereas R half, that as it is transferred to the new L half. So, that is not our part here. We need to understand that the structure which is available within the round here, we go for an expansion, because before going to that particular block, this block is key generation component of your DES algorithm, and this block is an encryption of your actual data. So, our data is going such a function, and finally it is encrypted and is getting as a ciphertext. But this half, what is going to the role of this particular half is only for key generation. So, already know you have 56 bit key, that means after removing the parity bit from the 64 bit, we got 56. This 56 is going to be divided into half, that is 28 and 28, left and right, and it go for a shift operation, and also it is doing some kind of permutation and combination, that is permutation operation, and finally it will be generating a ki. Ki is nothing but round key. Here we can note the size of the key is 48 bit. So, here the size is 48 bit key, the size of the key. Initially it was 64, and then the 8th bit is removed, then it is 56. After doing the permutation or the compression, you can see the shape of the block, which is compressed. The compression, we can able to get only 48 bit key. So, it is going to be happening for each and every round the same process. This process is going to be repeating. So, that is all about your key generation. Now, it comes to our encryption process. We already know that R, one copy is taken into Li, R minus I, Ri minus 1 is moved to the Li. What about this expansion here? Why we need to go for E table? This is what we say as a round. So, this comprises of one round, 1, 2, 3, 4. These 4 blocks is comprised of one round. Like that, there will be 16 rounds are available in your DES algorithm, and also it is f, which we have defined as a function. Now, why I need to go for expanding? What is the need for first step as expanding here is the size of block which is feeding into the round is only 32 bit, but our key size is 48 bit. where I need to expand this from 32 to 48 so that it can do any operation with respect to your key. So, if it is an XOR operation, here the 48 bit is XORed with your key, that is Ki is XORed with your Ri minus 1 as expanded version of your Ri minus 1. Then this 48 bit is go to the next level. So, first expansion, then there is an XOR operation with respect to the key, then it is go for the substitution where S box again it have to reduce to the size of 32 because actual size is 32. So, during the key operation there is a key addition XOR operation of key only, you need to have a 48 bit, later on it must be 32 bit. So, we can see that it is going to be giving a 32 bit after compressing the value, you can see that the compression where it is getting 32, and finally it is giving for some confusion with respect to your permutation, with the help of that it is getting the 32 bit value, and finally our left half is XORed with the actual result we obtain after the permutation, and new Ri is generated. So, now we can able to understand how each time the round is going to be generating from R I minus 1 to R I minus 1 to R, like that each and every time it need to go for such a operation. Parallelly the key has to be generated, totally 16 keys need to be generated from single key. This is what an actual process of DES algorithm. So, now we need to know about how this can be studied with the help of your simplified DES algorithm. So, this is what the operation, it is described with respect to this particular equation. Li is equal to Ri minus 1, Ri is equal to Li minus 1, L suffix I minus 1 XOR of the function of R suffix minus I minus 1 comma Ki. The key generation is again going for this permutation of selection, and there will be around 16 rounds, all these we know. But in the simplified DES, for the study purpose, we are going to consider the encryption operation takes only 8 bit block of plain text, where we can say in the case of our actual encryption algorithm DES takes 64 bit block. Now, for the simplified version simple DES algorithm, it is taking 8 bit block as a plain text. For example, you can see that here 10111101, that means totally 8 bits, and 10 bit key as an input and produce 8 bit block of ciphertext output. So, instead of having 64 bit block and 56 bit key, we are going to study this simplified DES with a smaller block of 8 bit size and a smaller key of 10 bit key size, where these two are given as an input. From that again we are going to get 8 bit block as the ciphertext output. The decryption also going to be the same process, where it is going to take 8 bit block of ciphertext and same key, because it is a symmetric key. During the encryption and the decryption it must use the same key, where it is taking 10 bit key used to produce the ciphertext as input and produce the 8 bit plain text as the output. So, what are the operations are already we know within a round, each encryption round process. For this simplified DES we are going to consider only 2 rounds, that is why we have 2 functions here. So, we have initial permutation function, because we say actual DES algorithm there are 16 rounds, here we are going to take only 2 rounds, function of f suffix k minus 1 sorry k1 and f suffix k2, the switch of key halves, and then final permutation, that is inverse of your initial permutation. This is what our encryption process. We have initial permutation and final permutation. Within the initial and final permutation there we have functions, we can say that it is a Feastel function, the switch of the key halves, that is key generation process. During the key generation process, there will be an initial permutation of P10 and it is divide the left half and right half parts, and also it is going for an 8-bit permutation resulting of 8-bit key and divide in the left and right part and double the left and so this step is used for the key generation in the simplified DES, where you have the simple DES algorithm with initial permutation P10 because we know the key size is 10. So, do the permutation with a table of 10 bits and dividing the right and left, shift and merge, and during the second round dividing and also 8-bit permutation resulting of 8-bit key, because we know for 2 round we require 2 keys of each size is 8-bit. Why we need 8-bit of key? Because the input block is only the size of 8-bit. So, we need to compress this 10-bit key to 8-bit key so that they can do an encryption process. So, now you can able to see one additional thing here in the round 2 is double left shift, here only single left shift in the first round. In the second round we have double left shift and merge and 8-bit permutation resulting of 8-bit K2. So, we should understand the difference in the first round, initial permutation dividing the left half and right half, left shift merge, permutation 8-bit resulting of 8-bit key. The additional thing we have here in the case of your second round is double left shift and merge, where you can able to get the 8-bit key. So, here we can concisely express this expression with the composite of the function initial permutation function K2, and also we can say swapping function K1 and permutation, initial permutation. The encryption algorithm, how we are generating the ciphertext is initial permutation and also the function 2 swapping function K of your initial permutation. So, first I need to do the plain text with the initial permutation, then I apply the function K1, that is your with the help of your key 1, and also swapping, then I will go for function K2 which is the key 2, and then inverse permutation is the last step. That is why we have to look from the inner loop inner brackets to the outer. So, we can able to see here this is our way how we generate the ciphertext. So, where K1 and K2 are the key for round 1 and round 2. We also able to note that here it is shift P10 of key, here we have 2 left shift which is the resulting key from K1 of this round 2. So, this is our overall structure of your encryption and decryption. So, we have 8-bit plain text for the encryption process, 10-bit key for the key generation process as an input key from the user. This is the secret key, it is only one key because it is a symmetric key algorithm. So, it is also used for encryption process. The other side of the block is showing the encryption process. So, we can able to see here P10 as the permutation of this and shifting, where I will generate K1 both which is used for encryption and decryption. Similarly, here double shift to get the K2 which is used for encryption and decryption. And one thing we have to notice here is during the encryption process I will start with the plain text and initial permutation, and the function is going to be the same, swapping is going to be the same, key is going to be same. Only thing is going to be changed here is here the initial it start with initial permutation and IP inverse, whereas in the decryption process we have to exchange, we start with the even the ciphertext with the initial permutation and the inverse initial permutation will be applied at the output of your plain text. So, here both the way it is going to be giving plain text as an input, similarly I get the output as plain text, but here you can able to see that 8-bit as the ciphertext. The key generation process as explained, we have left shift 1 1, then similarly left shift 2 2. So, we can see that it is going to be generating the K2. So, now we can able to see here the structure of your S box substitution box. that is your S box is given. There are 2 S boxes are required because 8 bit. How we are going to handle the 8 bit? We will handle it the 8 bit as 4 left bit and 4 right bit. So, with the help of the S box 0, we will simplify the 4 bit of left and similarly 4 bit of right. So, for that right 4 bit is going to be taking the value of S0 and S1, from that is going to be getting the value with respect to the 4 bit. Then we have a P10 box, P8 box and P4 box, where it is going to be used for key as well as the permutation of your input, initial permutation. Then we can say that this is with respect to your internal process of your round. So, we can see an example with respect to your key generation. If I am assuming that this is what the key, then the permutation 10 we are taken here. Suppose I want to say 1th bit of the key, it is equal to 1 is respect to 7. So, here 1 is moving to the 7th bit. So, 1, 2, 3, 4, 5, 6, 7. So, like that I will be mapping this 1 with respect to 7, 3 with respect to 1, 0, 1, 2, 3, 3 with respect to 1. Like that I will be swapping, then later on I go for splitting them into 2 half, then I go for shifting them left. So, 1 moves here, 0 comes this way, here 1 comes and 0 goes this way, circular left shift, where it is going to be rearranging the bit in such a way that for the generation of the key 1. And from this I am going for P8, where I have P8 here, that is P box. The first here P8 0, right, the 0 has to be the first bit, this must goes to for example here I will be rearranging with respect to the P, where I have 1 will go to 6, right. So, 1 will go to 6, similarly 2 will go to, like that I will be repositioning the value in order to get the value of k. Similarly, I do the round 2 key with the help of these zeros which is obtained from this k1. So, I am going to shifting them twice, right, twice to get the key value k2. So, then with the encryption process, again I go for a initial permutation, substitution function, then the expansion function. We can note down that here the initial permutation has 8 bit, they are rearranged accordingly based on this particular table used for encryption. But in the expansion table, where you can able to see here 4 1 2 3 4 1 2 3, only 4 bits are going to be rearranged, and also from this 4 bit we are able to generate 8 bit, which is nothing but your expansion. So, in the case of your initial permutation I am taking 8 bit, and these 8 bits are as given as it is according to the table how it is going to be rearranged. But in the case of your expansion, we know very well encryption, we are taking 4 bit. So, this 4 bit has to be expanded to 8 bit. Above where you can see that there will be 4 bit, but below you can see that 1 2 3 4 5 6 8 bit. So, from the 4 bit we are able to generate the 8 bit. So, from this we can able to say f is taken from 0, S0 and S1 such that R is expanded by E, the expansion is XORed with subkey, the 4 bits are input for S0, the last are the input to S1. So, you can able to see here first 4 bits are input for S0, as I mentioned earlier there are 2 S boxes. So, first 4 bit and last 4 bits are going to be given in S0 and S1. The input I1, I2, I3, I4, then I1, I3 is the row for looking into the S box, whereas 2 and 3, that is the first and last bit is looking into the row value, and middle 2 bit is used column value, where output goes to the P4. So, now we understood how this simplified DES process is working, and also how the steps are simplified we also able to understand the key expansion in your simplified DES. Thank you.